Hi, everyone. This is Paul Bemis. Welcome to another one of our webinars. This month, we're going to be talking about transitioning from fossil fuels to net zero in public buildings. And this is an important topic right now because, as we heard in our last webinar, when we talked to the Department of Energy last month, we talked to National Institute of Science and Technology. We know it can be done. The question becomes, how do we do it in older buildings? And we heard from Drew Crowley's presentation on decarbonization that the advice they're giving us is don't knock the building down, but retrofit the building. There is a lot of discussion about knocking things down, but the opportunity to take what we have and improve it is probably the lowest carbon option we have. And the issue becomes, how do we do that? So I'm excited to have with us today a group of people who have been through this and might be able to share their experiences with us. I'll introduce them in a moment. But first, let me point out this is a webinar and it's subject to technology coming and going and not always working. So if we have a technology problem, I'll just deal with it and we'll reschedule it or whatever we can do. If you want to ask questions as we go, I'm the moderator for the session today, and I will be interacting with the presenters as they present. So if you have questions, just put them into the question box in this little GoToMeeting, GoToWebinar session. There's an area where you can enter questions, and if you enter them, I will try to inject them as we go and make it more conversational that way, as opposed to waiting until the end for everything. We do have a lot to cover today, and we're going to try to do it in an hour because we're all busy. So let me go ahead and introduce the guests. I have three people with us today. Two at the moment, one hopefully is going to show up. Oh yeah, here he comes. So we have Troy Kerr and Jeff Oak. Is that how I pronounce your name, Jeff Oak?
It is, that's right.
Yep, and Tom Bowman. So Troy is the principal with a company called FGM Architects. They're out of Chicago. They work in the K through 12 space in the Chicago region. He's University of Maryland, University of Washington, St. Louis, work in educational institutions all along the way. In addition, we have Jeff. Jeff's with us as well. He is with IMEG. He's a client exec, oversees education in the science and technology sector. So he's got a close relationship with the customer in this case. And the third presenter is Tom Bowman. He's with his own practice called Bowman Design. He's a certified passive house consultant, an architect, and has been quite involved in this program as well. So I'm thrilled to have the three of them with us today. I'm now going to hand over to you, Troy, so that you can go ahead and present.
All right, thanks very much, Paul. So we have kind of a lot to get through here, but we'll do our best to go quickly. As Paul mentioned, if you have questions, please enter them in the chat and we will do our best to answer everything. We've also included our contact information at the end of the presentation, so you can always reach out and contact us directly as well. All right, so we're going to be talking about Prairie Trails School in Mount Prospect, Illinois, and the project that we did that transitioned an existing 1960s era school building into a high performance net zero energy facility. As Paul mentioned, I'm joined today by Jeff Oak and Tom Bowman. So Jeff is a senior principal and client executive with IMEG Corporation. They are the mechanical, electrical, plumbing, and fire protection engineers on the project. We work together all the time, so we're very close collaborators. And then Tom Bowman is the owner of Bowman Design. As Paul mentioned, he was our certified passive house consultant. Tom was an integral part of this process as well. And I'm going to lean on Tom to talk about some of the specific things that are unique to passive house and what that did for our project. So a little bit of background on Prairie Trails School. Prairie Trails School is in Mount Prospect, Illinois. So if you look at the map on the left-hand side, downtown Chicago is circled in green. O'Hare Airport is circled in blue. And then our site is circled in red. So we are to the northwest of Chicago. We're in a relatively established and kind of mid-sized suburb called Mount Prospect, Illinois. Our client is River Trails School District 26. and we'll talk a little bit more about them in a minute. But so the building itself, this site plan on the right, you can see it's a campus. So the school is labeled number 2, and the number 1 that's pointing to it is the district maintenance building that sits on the same site, but is basically uninvolved with the school. You can see from the diagram that we did land some solar panels on that building as well, and we'll talk about that in a little bit, but that was necessary to get to our production demand. So a little bit about District 26. So it's a suburban Chicago school district that services a little over 1,500 students at 4 different schools. So they have 2 true elementary schools, 1 middle school, and then Prairie Trails, the building we worked on, is pre-kindergarten and kindergarten. They're a pretty diverse community, 49 different languages spoken. Let's see, we'll kind of skip the per pupil expenditure, but they've always had a very deep commitment to the environment. They've done this for years. It's been kind of homegrown and really driven largely by their business manager. So all of their buildings are green ribbon buildings, as well as Energy Star certified. And they've been part of projects all over the map in terms of installing stormwater infrastructure that helps, filter stormwater, to solar panels, to better cleaning practices, you name it. So, and the real story for River Trails is that their dedicated staff is who made this possible. So, as I mentioned, their business manager has been kind of leading the charge, but they have a very dedicated administration and very passionate teachers, as well as a board that was very supportive of this process. So I'm going to turn it over to Tom for a minute to talk about Passive House, and then we'll get into the actual project itself.
Tom hasn't joined, Troy.
Oh, he hasn't? I thought you said he was on.
Nope, I got Jeff.
Okay, well then I will talk about Passive House since Tom hasn't joined. So Passive House, or what we call FIAS as its acronym, is an organization that originated in Germany, but it has a US branch. So we call it FIAS because it's the Passive House Institute of the United States. And they have a certification program that is really a 2-part certification known as FIAS Plus and FIAS Plus Source Zero. So FIAS Plus means it's a high performance building standard. The buildings themselves use significantly less operating energy than a typical baseline building. And Source Zero means that you do the FIAS Plus standard, but also generate the operating energy necessary on site. The standard itself is based on the modeling performance. So they did a significant energy modeling process as part of our certification. And then there's a second phase to it that is done during construction that monitors both the products that are used as well as the performance of the building through a couple of benchmark testing options.
Troy, just a question there on modeling.
Yeah.
Do you know what modeling method they used for this building?
So that was actually kind of interesting. So Jeff can talk about this a little bit too when he does his portion on the mechanical and electrical system. FIAS uses WFI as their standard, but the interesting part was that our design team did not. So trying to get those 2 programs to talk to one another was one of the challenges that we went through for this building program, because the results, while many of the things are similar, they're not precisely the same. So that was kind of challenging. Another thing that I will mention that was kind of an issue for us is that Passive House had some growing pains with us, because we are a school and Passive House is obviously originally a residential standard. So there were a lot of things about construction type, about scheduling that were not easily overcome. Because their modeling parameters and the construction details that they're used to seeing are not typically what we would use. They're more geared towards the way that a house is used. So that was kind of challenging, but we did work through it. So we had some parameters that we were working towards for our FIAS Plus certification. an annual heating demand of 8.3 kBTU per square foot per year, an annual cooling demand of 7.8, a peak heating load of 6.3 BTU, and a peak cooling load of 4 BTU. So one of the interesting things about FIAS is that there are 7 benchmarks that you can hit. You're allowed to miss on any one of the 7 in order to get certification. So we did meet 6 of their targets. Air tightness, this is another one that's really important. I'll just kind of talk on that. So because of the interest of the standard to maintain buildings that use a lot less operating energy, one of the big things that they focus on is air tightness. And that was kind of an interesting process, especially with an existing building. You know, that was probably one of the more challenging things, and we had some interesting things that happened to us along the way that we'll talk about. One of the things that Tom wanted to focus on that I think is really important because it helps tell the story of how we got here is the FIAS approach. So FIAS challenges you to start with as compact of a building as you can get. That was a little bit of a wrinkle for us because we were starting with an existing building, so we didn't control what the floor plate looked like, what the form of the building was, and it was a 1960s school typology in the suburbs. So it's, you know, 1 story, you know, lots of perimeter, you know, it was definitely not a warehouse or, you know, a multi-story building or anything like that, which would have been a little easier. But so if you start with a compact form, then the first step is to reduce the heating and cooling demand. So you do that through a good envelope, continuous insulation, a continuous air barrier. You try and manage your solar gains if at all possible. So exterior shading, although that's not what we did. And again, that was kind of challenging. And then also you do heat and energy recovery ventilation. So trying not to waste any of your exhaust heat or anything like that, or at least in our climate, it's primarily heat. The second step is to reduce the energy use. So we did that through an energy efficient HVAC system. You know, in a home, it would be a heat pump. In our case, we used VRF, and energy efficient lighting and hot water systems. And then you offset that energy use in the third step by using renewable energy. As I mentioned, we got the Source Zero certification, so we did all of our offset with renewable energy that was generated on site. So the baseline EUI of a building of our typology that we were working with was 75 kBTU per year per square foot, and our target was 24 to 26. So a little bit about this project. The project itself, the district had some growing pains. They had a building that was underutilized, they leased part of it to another organization, and they wanted to take that building back under their control and bring all of their kindergarten students to it, which would alleviate some pressure on their 2 elementary schools. But they didn't really have all of the money that they needed to do that. This district has always been very, very proactive about grant pursuit, and they found a grant that aligned with their sustainability goals from the Illinois Clean Energy Community Foundation. So the ICECF was willing to give a grant to a nonprofit organization of up to $2 million, assuming that they could meet some benchmarks. One, it had to be a net zero energy project. 2, it had to use on-site renewables. You couldn't purchase renewable energy certificates from anywhere else, so you had to do it all yourself. And number 3, it had to have no natural gas service, and it had to have a target EUI in the, what they said was low 20s. So we weren't sure exactly what that meant. So through energy modeling, we came up with a target of 24 to 26. Ultimately, what this means is that our carbon footprint reduction on this project through on-site renewables is 100%, and the savings to the district is about $30,000 a year, give or take, depending on the price of utilities. One, as I mentioned, we cut off the gas service in its entirety, so they're no longer paying for natural gas, and their electric use is 100% offset, so we've offset all of those bills too. It's not quite that simple because our utility still charges the district for service, even though they're not actually, you know, using that much of the utility. So it's not quite 100% offset in terms of that, but it is 100% offset in terms of use.
And Troy, at the moment, you're using no storage, right? So you're using net metering to flow that energy back and forth, right?
Exactly. There's no storage in this building, but our utility, the state of Illinois, does require net metering, so distributed generation from the utility. So net metering is definitely an advantageous thing that we have here going on for us. And this is just an aerial view of our building, just so you could see. This is kind of, I felt like it was a good thing to look at. It's got a pretty good view of all of our PV panel array, as well as our DOAS units on the roof and things like that. So you can kind of see the form of our building there. So it was completed in the summer of 2021. It opened for the start of school in August of 2021. It is net zero energy. It's kind of unofficially net zero. We just completed our first year of monitoring, and now we have to go through the verification process. Again, there's no natural gas service to the school, and our target EUI was 24 to 26. You'll see what our actual EUI was a little later. Just a quick overview, because we'll talk about all this stuff, but basically everything was replaced. So the building was built in 1966. It was a typical mid-century brick and block elementary school. It had a hot water boiler, and it was built with no air conditioning. Later, through wall air conditioners were added. It had single pane windows. It had galvanized domestic water piping. Everything was original. The electrical service was original. One of the two boilers was original. The piping was all original. The windows, you name it, everything was basically the way it opened in 1966. So when we talk about systems replacement, we're really talking about the entire thing. So we kept the part of the shell of the building and basically replaced everything else. So Jeff will talk about this, but the real highlight of the show here is the our mechanical system and our BAS system. So we use load specific electrical monitoring. So we are monitoring HVAC loads, plug loads, lighting, those types of things. And our BAS system, as a requirement to the grant, is available to be viewed online, so that it has points that they can see as part of their website that they can link into, so that they can share with the public the performance of the building. And it's really pretty sophisticated.
Who's the supplier on the BAS, just out of curiosity?
It was through Train.
Yep. Okay.
So we did all LED lighting throughout the building with light harvesting to reduce energy consumption. And you've seen our new PV panel system. Mm-hmm. So the PV system had a production target of 227.1 megawatt hours, which did include a buffer, which was a requirement of the grant. And actually, you'll see when we talk about energy performance, that was important, because PV panels can be very inconsistent in terms of the amount of production that you get. So, all right, so the existing building, a few images of it, like I said, very plain Jane, mid-century modern building, brick and block, single pane windows, very thin roof insulation. This roof happened to be put on in the 1980s, but it was a tar and gravel roof. So, it's probably not dissimilar to the schools that most of us would have attended. And what we did was to basically, we kept the block and we kept the roof structure, and we did everything else new. So the existing walls had no insulation. We took down the brick. We put up new stud framing, new gyp sheathing and air barrier, new exterior insulation, and fiber cement siding. So the code requirement would have been an R20 on our walls. In our zone, what was actually installed was a continuous R24. There was no existing air barrier, but the code requirement there would have been 0.4 CFM per square foot. What we installed was a 0.04 CFM per square foot. Roof insulation, as I mentioned, the existing was put on in the 1980s. That was about an R4. It had 3/4 of an inch of rigid with then tar and gravel on top of it. Our code requirement would have been R30, and here's probably the most dramatic increase. We did an R65, so the tapered insulation that we put up there was 10 inches thick at the roof drain. and it tapered up to over 2 feet thick at the roof edge. You can see this is an installation photo while the roofing was going on. Those are 5-gallon buckets sitting next to a completed area of roof sitting on the roof deck. And you can see that the insulation thickness is taller than a 5-gallon bucket.
This is rigid foam, so this came in sheets, or is that how that worked?
That's correct. So it's sheet polyiso
Yeah.
with an EPDM roof on top of that.
Mhm.
And then lastly, the windows, the existing windows, as I mentioned, were single pane, so we consider that to be really no true U value to that. The code requirement would be U.38. What we did was a triple pane glazing, argon filled in a double insulated curtain wall instead of a true window for a U value of 0.12 at our windows. So you can see how we took the existing window openings, opened those up, and put that new curtain wall framing in there. Part of our project included a requirement to educate both the public through the website, but also the students of the district about what we did. So part of the way we did that was to engage a designer for museum exhibits. This was one of the exhibits that they came up with. It's essentially a 3D model of our new wall assembly. So the way that we treated the exterior wall, it's built inside the building, obviously, but we started with the existing CMU, added metal studs and gypsum sheathing. We did a fluid applied air barrier, then the continuous insulation, a thermally broken rail system, and then our fiber cement siding on top of that. I'm going to turn it over to Jeff to talk about mechanical and electrical systems.
Sure, thanks, Troy.
Mm-hmm.
So when we started the project, we wanted to go through, many different system options with the district. We wanted to align not only their energy goals, but also make sure that, they could maintain it. It would provide a comfortable environment. And there was a lot of different pressures from FIAS and the school district and the grant. And so we wanted to make sure that we were looking at a bunch of different system options. As you can see here, we looked at the baseline code system, which is a pretty traditional boiler, chiller, unit ventilator system. We looked at geothermal. There was an adjacent school district that utilized a single pipe geothermal system. That wasn't our highest recommendation. We typically design 2-pipe geothermal systems, but with the adjacent district doing a single pipe, we did want to at least look at that for them. So we looked at partial hybrid geothermal as well as full 100% geothermal. And then we looked at coupling that with a VRF system, hybrid geothermal and full geothermal, and then just a VRF air-cooled system. And we looked at the impact that had on the EUI and the energy cost and kind of the maintenance considerations and the first cost. And we ended up selecting the VRF air-cooled system. It really came down to a decision between the VRF air-cooled and the VRF 100% geothermal. Obviously, the 100% geothermal would have been more, saved a little bit more energy, but the amount of increase in cost to go from VRF air-cooled to VRF geothermal was pretty dramatic, and we would not have seen a reasonable payback. And so that's when the VRF air-cooled was selected.
And I'm assuming, Jeff, just before you go, that the reason that is true is because you've got to drill boreholes and put piping in, and that drives up the upfront cost. Is that correct?
Correct. Yeah, the cost of the geothermal field, I guess I'd have to remind myself, it's been a few years since we looked at it, but just the large cost of all the bores, and then coupling that with the water-cooled VRF system, just would have put the cost, pretty dramatic. And if you look on the right-hand side, the energy cost difference between the air-cooled and the water-cooled, give or take $7,000 per year. If the geothermal field would have cost in excess of, $300,000, you could see that the payback on that would have been, a very long time.
Mm-hmm.
Okay.
So, as I mentioned, the system that we ended up with was, dedicated outside air system coupled with a VRF. So we have multiple, the floor to floor height, or sorry, the floor to structure.
Yeah.
This building was very tight. It was constructed to house unit ventilators that, don't have any ductwork above the ceiling. And so we needed to be very, careful with, the size of ductwork we were routing to maintain reasonable ceiling heights. So in this particular case, we had, as you saw from the picture before, and there'll be a picture coming up that shows the roof We have multiple dedicated outside air systems to serve, up to about 3 classrooms each, and that's to keep our duct sizes lower and our static pressure losses lower. And so each of those dedicated outside air systems has energy recovery built into it and provides all of our code required ventilation for the space. And then we have terminal cassette units located within each classroom or within each office that provides heating and cooling through the variable refrigerant flow system.
One thing I'd like to just piggyback, if I could, for a minute, Jeff. So we were, going through this delicate balancing act of what was the most efficient way to deliver the mechanical versus what could we actually achieve in terms of ceiling heights. As Jeff mentioned, we had very tight floor to roof structure clearance. I think it was just a little over 9 feet. But so what we landed on was, like Jeff said, 3 classrooms being served by a DOAS unit. And what that meant, when we look at the aerial again, you'll see we had more DOAS units than we actually probably needed, but because of that duct run size. And what that had an impact on then was the amount of roof that was available for PV panels. So there's always going to be kind of this give and take about, the number of units, the size of units, and what that leaves over in terms of what's available for the solar panels.
Right.
Yeah, that's a good point.
Mm-hmm.
So dedicated outside air systems, most of you are probably, pretty familiar with these. Each of them can, contain ECM motors. They did have full energy recovery. We brought all the exhaust through these units to recover the energy from the exhaust, to transfer it to the outside air that was coming in. Digital scroll compressors, and then heat pump heating. Each of the units did have, supplemental, supplemental heating coils in them. That was a little bit for 2 reasons. One, to consider to be able to heat properly in the very low ambient conditions that Chicago can see. And one thing to notice, a little bit of a lesson learned, and we'll talk about this in a little bit, but there was a few of the units that when we first started the building and we were operating, we noticed our energy was a little bit higher than what we had anticipated. And when we started digging into it, we found that there were a few of the units that were defaulting to the supplemental electric resistance heat as opposed to running on the heat pump heat. And so that's why you'll see in a couple of minutes, a couple of our first 2 months, we weren't operating nearly as efficient as we had hoped. And that was one of the reasons why that we had found.
Yep.
So as Troy mentioned, those dedicated outside air systems, we have kind of 1 for about 3 classrooms. You can see from the aerial we have was, 1, 2, 3, 4, 5, 6, 7, 8, 8 of them plus a unit that serves a multi-purpose room, which is great. Gives a lot of redundancy and reduces our duct size. But as you can see here, it does reduce the amount of roof area that we have available for PV panels.
Yeah, one really important part for this was that our zoning requirement was that every unit had to be screened, which increased the footprint of the units themselves, which also increased their shading. So that had a big impact. You can see kind of the no-fly zones on the roof where they couldn't go because of shadows with the PV panels, where they were inefficient. So that was kind of a challenge. That's why we ended up having to land panels over on the maintenance building, which you can see in the background of this image kind of across the parking lot. We talked to the ICCF, the organization giving the grant, and they were accepting of this, that we just didn't have enough roof area to meet the energy demand. We talked to the village. They would not accept ground mounted panels from a zoning perspective. So we ran conduit underneath the parking lot, which was replaced as part of this project too. So it was open and connected the PV panels on the maintenance garage to the building system.
What did you end up for? Who's the manufacturer on the DOAS system? And Jeff, you said it was, you were using some of the heat pump in that system too when you didn't want to be. You had a coefficient of performance 2.3 on that unit. So first, who was the supplier on the DOAS unit? Is it Train?
Yeah, Train provided, the school district has a very good relationship with Train. So they provide the majority of the equipment and the controls on the system.
Yeah, so Train actually did not only the BAS and the mechanical, they also were the provider and installer of the PV panel system as well. So getting the interface between the BAS system and the PV system was pretty easy, all things considered. So
And what about structure? I mean, schools I've been involved with, there's these DOAS units are heavy. Did you have to do structural?
So our structural engineer did an evaluation of the existing structure, and they didn't think that it was necessary. So we did really no real reinforcement. There was a little bit of spot reinforcement in locations of the existing joists, but yeah, we kind of got lucky, including because of the weight of the roof that was taken off. Things like the added PV panels didn't require any additional structural support either, because that tar and gravel roof that we took off was so heavy. The structure was already designed for more than what we put up there.
Just out of curiosity, Troy, were there any prints on this building, or did you have to kind of redo it? And a lot of times I'm finding these old buildings, there's no documentation on them. It's hard to tell.
Well, yeah, that's kind of the MO for our practice. As you mentioned, we do FGMA does schools and other, community institutions. We do village halls and police stations and stuff. My practice works exclusively on schools, and for a lot of these mid-century buildings or even earlier, there's very little documentation. Even if the district happens to have the drawings, they weren't very robust. But in this case, we had a few things, but not very much. So it really relied on field survey and confirmation. But it's not that big of a building either. It's just about 29,000 square feet, so it's pretty manageable.
Mm-hmm.
But yeah, that was definitely a challenge.
And how did you attach the solar arrays? Are they clipped? Are they screwed? How did you get them onto hold them onto the roof?
They're loose laid ballasted, so they are ganged together on a metal structure. Basically, any one of these kind of blocks that you see of the PV panels in the photo are all kind of tied together on a metal structure. And underneath every panel are two concrete blocks sitting on a metal sled that's attached to that metal structure. And so that has an implication too on the angle that the panels can be at. So there is a maximum angle that you can hit with a loose laid panel, which is obviously for our location, at least. We're not in the Caribbean or anything, so it's, we're shallower than would be normally efficient. But if we wanted to go steeper than what we had mounted, we would have had to do structure mounted, which would have been a lot of penetrations through the roof, especially when it was kind of performance contractor installed, as opposed to part of a bid package where it could have been coordinated with the installing roofer. So
yeah. And you talked about windows. Did you end up reducing the window area compared to what it was prior?
No, we actually increased it, and that was one of the pushbacks that we had with FIAS. They wanted us to, during their initial review of the project, they wanted us to reduce the overall window area, and we added some skylights too. So there was a lot of give and take in terms of, back and forth about the energy model, and well, what if I agreed to get rid of the 3 skylights on this side? Would, do we get there? That kind of stuff. And so that was one of the challenges. Again, with it being a residential standard, reducing the size of the windows is not that big a deal. A lot of people's houses, in their bedrooms, they're not doing a lot of reading or working necessarily in their bedroom. They're there to sleep. So it's okay to have smaller windows. But in this case, we were very interested in the correlation between natural light and student performance and employee health. And so we were really pushing for large windows, as well as, I don't know if you saw it, you can kind of see it in this picture. We have a direct exterior exit door out of every classroom that did not exist previously. That came through conversations during design with the local police department about how they wanted the building to function in the event of an emergency, God forbid, something like an active shooter or something. They requested to have
we're having to design
exits
for that now.
Yeah. And so that was a real pushback too, because door performance is really challenging. The best door is not nearly as good as a window, and a window is not nearly as good as a wall. So from a air leakage and thermal performance, that was kind of challenging too. Right. I will say, since we have doors, that's a good point. All of our windows are triple pane glazed. The doors could not support triple pane glazing, so the doors are double pane glazed.
Mm-hmm.
All right, we'll keep going here.
Then a couple last, obviously we did very efficient lighting, and then domestic hot water. All of our all our light fixtures are LED. We're controlling them off, vacancy sensors where we can, or occupancy sensors where needed. The domestic hot water loop, pretty common, is that pump is run on demand, as opposed to kind of continuous as the building is operated. And then measurement and verification of electrical panels for energy monitoring. So we're constantly measuring our lighting loads, our HVAC loads, our plug loads to kind of look for variances in the system, and that helps us kind of commission the building as it operates.
I want to take a minute and talk about some ongoing maintenance considerations too, because these are conversations you guys could probably have with your clients, or if there are any building operating engineers on the call. There's more inspection and tune-up requirements on all of these units to make sure they're operating properly. Again, our building had a grant that was contingent on us performing at a net zero level. So there was a monetary stake in it, but even if it's just a philosophical stake that you have, there's really a lot of work that goes into making sure that the building is operating properly. As a school, it's been particularly challenging for the district because there are so many different people who feel like they have dominion over their space, right? Teachers can be, very territorial cavalier about the way they operate. I like to bring my kids in through the door in my classroom. Well, you can't do that. It doesn't have a vestibule. It's not designed for that. So there's been a lot of monitoring that has had to go on, and a lot of correction. But we found that people have been pretty compliant about it by having load specific electrical monitoring in the building. They can really see what people are plugging in, Christmas lights and lava lamps and stuff. We like to joke, no more of those, no microwaves in the classroom, those kind of things. But there is a lot of stuff to check. Door thresholds were a real challenge for us in terms of the envelope performance, because trying to get one that was thermally broken and performed well in a climate like ours was really challenging. Mechanical dampers, that's actually a really interesting story. So I mentioned we would talk about this. Part of the FIAS requirement was to do a blower door test during construction. And initially our building actually failed the first blower door test. What we found out was that the exhaust dampers within the DOAS units were being forced open by the blower door testing equipment.
Oh, I see.
And we were losing air through the exhaust dampers. So we had to add some points to the BAS system and add motorized dampers that when the unit was running, it actually drove the damper shut instead of just passively falling shut. So that was kind of a lesson learned. I as an architect, I focus on building envelope all the time. I never thought that the mechanical unit would be the place where my building envelope failed, but it raised some interesting points.
Yeah, it is a system after all, and this is an issue. This comes up quite a bit. This issue of complexity associated with these new designs. They are fundamentally more complex than the binary oil burner that we've used in the past, right?
Absolutely. So another thing to consider is that really paying attention to what the BAS system is telling you is going to be really critical. Your clients or operators will need to be paying attention. And really, I would say, Jeff can comment on this, but IMEG has had to pay much more close attention to what the BAS system is telling us than they would typically do, because that was how we managed to catch, as Jeff mentioned, that the resistance heaters were running in the first 2 months. The BAS will tell you what the energy usage is, and it will tell you what the energy usage was anticipated to be and where that might fall short. So you really have to pay attention. I know one of the things, I got a call from a young man that works with Jeff over Thanksgiving that was concerned that the units were operating at full tilt even though the building was closed, and could we call the owner and see what was going on? Because in a net zero facility, really every hour counts. The important part for net zero is to work on scheduling, because you can control system behavior as much as the design will allow. What you can never really control is human behavior. So it's really making sure that the end users are aware of the amount of time they're allowed to spend operating the systems, the way that they keep doors open, the way, those types of things. Like in our school, for example, we found that drop off and pickup were a real challenge. We did not anticipate that they would keep the doors propped open for 40 minutes every morning and 40 minutes every afternoon.
Wow.
And so there's a spike in our energy usage if you looked at a daily energy use that we didn't anticipate, once at 8 a.m. and another time at 3 p.m. And that's because of that door opening, and it's probably something that we really should have considered, but it's a lessons learned. We got lucky and we had enough cushion built into the system that we were able to overcome that, but really it's a big deal.
And what about modes, modes of operation? You have, occupied, unoccupied. Do you have more modes?
No.
Jeff, do you know what's built into there?
Yeah, no, typically we're occupied and unoccupied. What we've learned a little bit is, certainly we have allowed the system to offset its temperatures and, reduce its, temperature set points during off hours. We are studying very closely that the energy impact on that. Sometimes we're finding that, the spike in energy to get the building back up to temperature has been higher than we expected. But certainly the dedicated outside air units do turn off. We don't run any fresh air. We really watch our vestibule temperatures. We're not keeping the vestibules at 70 degrees. I believe the set points in those are down at 60 degrees. And so we only really have 2 modes of operation, but we are studying the energy impact as to whether we just maintain normal temperatures with the outside air off, or do we allow those to be reset. As Troy mentioned, we have met the yearly net zero, but we're still looking at how we can improve this building overall from its performance.
Yeah.
And one thing, commissioning, guys, did you do full commissioning on the building? It sounds like you must have. You did blower door testing for sure.
We did. Yeah, we did full commissioning, and I think they caught a lot of the items. But like we said, one of the items that was not caught was, I guess this is a good time to talk about this. So if you look at the chart that's shown here, to the way left is the start of the year in January of, what would that be, 21?
22.
No, 22, thank you, January 22. And then to the right is January of 23. And so on the left in the blue indicates the amount of energy that we used. And so you can see that we're much higher than what we had anticipated in the gray. So, when we were starting to look at this, we're, in blunt words, we're kind of freaking out a little bit. Why are we using so much more energy than what we had anticipated? And there were 2 real causes to that. One is the one that we had mentioned before, that we were using the electric resistance heat in the dedicated outside air systems as opposed to the heat pump heat. And then secondly, the building automation system was not aligned with the utility, and it was, the utility was reporting incorrectly. And so that impacted our total energy usage, and we're working on correcting that now. But as you can see, even with those 2 poor performing months of January and February, if you look over to the right, our actual usage had an EUI of 27.24, and our solar production for a full year was 29.33. So even with those poor performing months, we are still officially net zero for the year.
Right. So I would add, those 2 months early in the year, there are lots of lessons learned that are built into this graph that we could go over. One, the BAS system. So I mentioned we opened for school in August of 21. The BAS system was not set up to carry over from year to year. So it reset on January 1, which was a problem because our grant is contingent on proving that we are net zero through the BAS system. And so then it basically stopped looking. So we had to correct that. As Jeff mentioned, we had some problems with the way that things were operating, mechanical units and stuff. He mentioned the electric resistance heat, but another one, like I had said previously, was that the doors were open for long periods of time, and then those vestibule heaters were constantly struggling to keep up their set point temperature based on 40 minutes of 10-degree Chicago air being let into the vestibule, right? So
yeah,
that was kind of a challenge.
Your environment in terms of weather is much like ours. That's part of the reason I wanted to talk to you. We're in New Hampshire, of course,
Probably
Were
not
the
dissimilar. Yeah.
not dissimilar, right? And the VRF systems were selected to provide 100% heating at those extreme temperatures?
Yes. Yeah, the VRF does have, 8 years ago or so, they did not have AHRI ratings down into extreme cold temperatures, but now those HRI ratings are available down to like -28. So we knew what performance we would get at the various temperatures. But we do have a little bit of supplemental heating in the dedicated outside air units to supplement that.
And Jeff,
And
just back to model, what model are you using again here in the gray? What's your energy model? What did you end up using for a model?
So Alex Zero is our energy modeler, and he traditionally uses train trace.
Yep, yep.
so a couple other things to point out here. The green is our solar production. You can see in the early part of the year, we had a spike of a couple of days, but most of our solar production was effectively nil. So this will be important for you guys in your climate as well. With that low slope of the PV panels, any snow and ice builds up on those. Cleaning
Right.
it off voids the warranty. So if you have a long winter, expect that you will have significant periods of time where your production is zero or pretty close to zero.
Yeah.
So we were really relying on the summertime to make up for that kind of winter doldrums in terms of energy production. So it's good that we built the buffer into the PV panel design, because we ended up needing it. As you can see, we are net zero, but not by that much, so
Yeah.
it wasn't that comfortable.
Yeah.
So
Yeah. Excellent. Excellent. You did it, guys. You did it. I mean, pretty challenging taking an old building like that and making it.
well, we think that the lesson here is that it can be done.
It can be done.
And it's not insurmountable. It's technology that's available on the market today. It's building practices that are not, they're not uncommon. It's the things that we do all the time. Now they have to really be done well, and it really requires an added level of oversight and testing to make sure that things were done the way that they were designed, making sure no corners have been cut. But if you do that, it is achievable. It's there.
So I'm guessing here what you must have done with your construction team is hold them to certain specifications. Say, listen, we're going to blower door test this at the end, and if it doesn't work, you're on the hook for that, right? I mean, you must have held their feet to the fire on this.
Correct. And it helped to have that passive house certification element in that regard. So passive house required, again, like I said, there was a rater verifier separate from Tom Bowman, who came out throughout the process. They were reviewing submittals, they were doing site visits, they did the blower door testing. So that helped to have them on site, really looking over everybody's shoulder, kind of that third party. They're not really the architect, but they're not really the owner. They're just this other organization. Also, our construction manager that worked on this project was a good partner for us. They sent their site superintendent to passive house training. So the site superintendent was really on board with what was required, and
that's called buy-in, when you get the guy to go to training. Yes.
Yeah, he was a bulldog about it. But like I said, it's things that we normally do, but just to the next level. Like the anecdotal story I like to tell is that to get the envelope to pass, any conduits that passed through the exterior envelope, had to transition from metal to plastic, and then the conduit had to be caulked shut once the wire was pulled through it, because that was enough of an air leak to have compromised the envelope. So
metal to plastic and then caulked shut. Yep.
Yeah,
makes sense. Your DOAS units on the top, resistive elements in there. Now I've seen, like, I'm working on one situation where there's a heat pump in there. So yours had resistive elements, and you had to control that point vis-a-vis your VRF systems through your building automation system so that they didn't come on. Is that what I got to?
That's correct. Yep. Yeah,
but there is heat pump in those DOAS units as well.
There is.
Yeah. So their typical operation is off of heat pump. The electric resistance is supplemental heat.
That's right.
Past the threshold.
We just wanted the default heat to be the heat pump, and unfortunately, in the first couple of months, there was 3 or 4 of the units that were defaulting to the resistance heat first. as
And
opposed
that's a controls issue, isn't it, Jeff? I
It's a
mean,
controls
fundamentally, it was just thinking that it needed to be there, but didn't, because the VRF system was taken. You had two systems, you just had to control it.
correct. The other thing I wanted to mention is, Troy had mentioned this a little bit earlier, but our team really, there was a lot of grant money at stake here, and obviously a very good client. And then obviously our team was just very interested in achieving this goal. So in order to really make it happen, just wanted, especially to this group that in similar positions to Troy and I, the amount of time that our team was in their office looking at the building automation system on a building that was already up and running, and the client was happy, it was operating well, but we really had to stay on top of it. Like Troy had mentioned, our one guy had found that over Thanksgiving break, the units seemed to be operating still at full tilt, and why was that going on? And it just really took a lot of oversight and scrutiny and supervision of the building over the course of a year to make sure that we hit our goal at the end of the year.
Well, and you're also going to have to teach the people who manage that building. I mean, you're not there every day. There's a facilities manager there somewhere, and we're going to need to bring them up in terms of their level of understanding of the system, which isn't a small task in many cases, because
Exactly.
they're not trained to do it. They don't necessarily know about this stuff. It doesn't mean they can't be trained. It's just that they're not. So yeah, that handoff is going to be important, I think, as we move forward with these projects.
Definitely.
So let's talk about cost. What did it cost to do this building? I mean, what was the budget?
So I hesitated on putting cost into this presentation because of the wild swings that have happened with the market.
Yeah.
But so the building was I'm going to misspeak because I took my slides out of here. If you give me a minute, I can bring up my cost information.
Mm-hmm. The reason I ask, while you're getting that, Troy, is that the feds are just now supporting this sort of thing. I think you've seen the material out, and they're getting ready to put a bunch of money behind this as part of the bipartisan infrastructure law and also the Inflation Reduction Act. They both. So DOE, as you're probably aware, is encouraging the kind of work that you just successfully implemented, and they're willing to fund it. So there's that. Now that's targeted. It's always targeted. You got to compete for it. It's grant money, et cetera. But there's also this thought that that's been kicking around. I'm sure you've already thought of, is that these things basically pay for themselves. That if you go to a school and you say to them, listen, your variable cost for fuel is going to go away, and so therefore the $30,000 a year you're spending on fuel cost is going to disappear. These things can be self-funding. I mean, you go to a bank and show them that, and you can self-fund them. Do you see that happening at all, or the possibility of that happening?
I think the possibility is there. It definitely depends on your project typology and any limitations on the funding that's allowed. But yeah, I think it is possible, because it's definitely not insurmountable. So I put up the costs as they were in kind of November of 2020 when we completed. We were probably about 50% of the way through construction. All the bidding costs were in there. Now this project, I will tell you, had a significant site cost associated with it as well. So there was stormwater infrastructure. It had a permeable paver parking lot. Again, the client is very environmentally conscious. So this is maybe a little skewed because of that. But you can see here the total cost, not including the grant, was just shy of $11 million for a 30,000 square foot building. So if you did include the grant, it would have been about another $73 a square foot. So we were coming in at about $380 a square foot without the grant, and it would be a little north of $450 a square foot for the renovation if the grant wasn't included. So
Yeah. A big part of it here was also the roof. I mean, you went thick on that roof. That has a really high R value. You really restructured the whole thing.
Yes. So trying to limit the energy usage was a primary aim of this project. We would do most of those things anyway, but just not to that degree. So it just shows you that going above and beyond what the code minimum is can really pay dividends. If we hadn't done that, I don't think we would have been able to get to net zero. Right. Originally, before the grant was confirmed, we were looking at possibly having to do 2 different designs, a passive house design and a non-passive house design, because if the grant was not confirmed, the client wasn't necessarily going to go with passive house. And we thought we could do it, but now that we've got a year's worth of performance under our belts, I think it's pretty obvious that it would be challenging to get there.
Now, Tom's with us at this point. One question
I
did come in.
apologize. You know, I neglected that look at that little Eastern Standard Time.
Yeah,
and,
I figured that was it.
Ready to get started, and
you're in
then
Chicago.
I noticed I had an email from you. Where are you?
We're in New Hampshire.
Yeah, so I want to touch on a couple of things that Troy was just repeating. So I assume he kind of spoke to the couple of slides that I put in there about the FIAS process. And generally, as far as FIAS was concerned, you know, I came into the project when they were already at 100% design development, but they were already doing all the things, and it really was just what Troy described. It was a matter of just needed to push a little harder. So he had maybe 2.5 inches of insulation on the exterior. We up to 4. We kept adding to the roof, mostly because we really had no other place to put it. And we had a case in this instance where we had a slab on grade, an uninsulated slab on grade, which we paid a penalty for and presented some challenges for us. So we really had to put the insulation where we had the opportunities to do it.
Yep.
And with
One question did come in here, Troy, about soft costs. What do you mean there by soft costs?
Soft costs would be our professional fees,
yeah,
testing, engineering, architecture, those types of things.
Yeah. And what about payback? So we're looking at a project of, let's say, 13 million, but you're saving $30,000 a month. So, you know, if you just do that math, it's like 4 years. I mean, it's 5 years, isn't it? I mean, the payback on this is fairly quick, isn't it?
Yes, absolutely. And I think that's why some of those, you know, comparisons that Jeff and his team at IMEG did for us in terms of the mechanical systems and possibilities were really helpful, because while the VRF may not be as efficient as it is available, it's definitely cost effective for the efficiency that you get. So
and how have they performed in cold temperature? Have you been able to sort of get a quantitative feel for comfort from occupants?
Yeah, and the kind of anecdotal evidence is that the comfort is significantly better than any building that any of those teachers have ever been in before. We did give them thermostatic control in every classroom, so you know there's no dummy thermostats or anything. They actually do have it. We were a little skittish about that, but the owner wanted to give that to them. You know, we kind of wanted to set them a deadband and let them operate, you know, but the owner wanted to give them thermostatic control, and it's been okay. Everybody's pretty happy with it. And the one thing that I will say, I don't know if there's anybody on the call that works on schools, it is astounding how quiet the system is, which from a learning environment perspective is really important, you know, the acoustics of a classroom. And
now,
that was kind of
that's interesting, because the compressor is, you know, when you've got an air source heat pump, that guy works, that thing works really pretty hard at 10 degrees out, you know, Fahrenheit outside. That thing's really working hard. But you've got 10 inches of foam between the compressor and the classroom, so you don't really hear
minimum 10 inches. Yeah.
That's the base layer.
Yeah, so it is pretty well insulated in terms of sound, but you know, compared to what a typical unit ventilator would have been, it's incredible how quiet the system is. So that was kind of an unintended benefit, a happy accident, if you will. The other one that came up because of the time period and the time frame that we opened this building is that the amount of outside air, the air changes per hour through the DOAS system, were a huge benefit during the pandemic as well. So
I work in air quality, so I'm quite familiar with that. In fact, I'm working on one project right now, and we are using the funds from COVID, ESHRAE funds. We're putting in dedicated outdoor air on the roof, and that one would also like to do the same thing that you're doing here too as well. I had a question come in about the VRFs. When the condensing unit is in defrost, how do you provide heat?
Yeah, so it's sized to handle that, but yes, that was a concern that we worked really closely with Trane in the controls and sizing of the system to be able to maintain temperatures throughout. So you're working at a reduced rate, but we did take that into consideration when sizing and selecting the units.
And the temperature of this building does not drop very quickly if anything shuts down for a while. It's got a lot of thermal mass. It's extremely well insulated.
Yeah.
You know, it's actually amazing when you put these triple glazed windows in. You know, they don't feel you don't feel radiant cold. They're not cold to the touch. They don't feel like there's a little coolness out. And there's a good expanse of windows in all these classrooms. It doesn't feel cold. You touch these, and it just doesn't feel cold. So that level of insulation really makes a big difference for the thermal comfort without the radiant losses to the perimeter.
In my experience, what it does is it gives you a very uniform temperature distribution everywhere in the facility, and it doesn't change very much based on outside condition. Yeah.
Mm-hmm.
Yeah, it's got a lot of thermal inertia. Yeah.
Well, okay. Well, this has been great. I really appreciate the time that you've given us today and answered these questions. Most of the questions that are coming in, I'm just relaying to you as they come in. So I think you've covered most everything we have. I would love the opportunity to reach out to you if that's okay.
Absolutely.
Yeah.
Absolutely. As I mentioned, you know, our contact information is here at the end. You can reach out to any of us. I'd be happy, Paul, to share this presentation with you. You can share it out to whoever might be interested in it, and please feel free to reach out to us.
We typically do. I typically pass a PDF along if people want to see it in case they want to reach out to you. We're in the same geography of you as you. We've got the same problems as you. We're not unique in that regard. It's that, but we are much like you in terms of latitude and cold weather. So we have to.
It's not San Diego, that's for sure.
It's not San Diego, and we've got humidity to deal with as you do and all. So we live in a similar climate and are solving similar problems, and it's nice to have friends, if you know what I mean, that we can consult with occasionally and go, have you ever seen this? And what do you do?
Yeah, absolutely.
Well, thank you, Troy and Jeff and Tom. It's been great speaking with you today. I appreciate your time, and we will be in touch. And yes, Troy, if you could pop over a copy of these, I'd greatly appreciate it.
I will definitely do that. Thank you very much for having us.
Okay, thank you. Bye.
All right, take care.
Bye now.
Thank you.